Welcome to the SAMPE Q&A session for additive manufacturing, and thank you all for joining us today. I would like to make you all aware that this session will be recorded and posted on the SAMPE website for on-demand viewing. If you have any questions throughout the duration of the session, please type them into the Q&A feature found on the control panel in the Zoom meeting window. With that, I'm moderating today's session. My name is Eric Schmid. I'm a product development engineer in the R&D group at Raven Industries Engineered Films in Sioux Falls, South Dakota. I'm also finishing up my PhD in composite materials at the Composite and Polymer Engineering Laboratory at the South Dakota School of Mines. I have the pleasure today of moderating this panel on additive manufacturing. We have 6 panelists today joining us to answer a few questions about their research in their technical papers that were submitted as part of the SAMPE conference this spring, which we are now hosting virtually. So thank you all for joining us. I'm looking forward to hearing more about their work. Our first panelist today is Huynh. Anne received her bachelor's degree in chemical engineering at Drexel University. She has stayed at Drexel to pursue a doctorate, also in chemical engineering. Her work focuses on developing and understanding fundamentals about thermosetting resins used in stereolithography processes. The title of her paper is High Performance Materials for Mask Projection Stereolithography via In Situ Sequential Interpenetrating Network. Our second panelist is Dr. Furkan Ulu. Dr. Ulu finished his bachelor's degree at Sakarya University in Turkey, mechanical engineering at North Carolina A&T State University, focusing on composite materials. He finished his PhD in nanoengineering, also at North Carolina A&T State, with his research being on 3D printed nanocomposite materials via additive manufacturing. The title of his paper is Digital Design for Voxel-Based Additive Manufacturing and Part Characteristics, Software to Printer Hardware Translation, Correlation, and Effective Software Solutions in Polyjet Printing. Our third panelist today is Oluwasola Arigbabowo, a graduate student researcher at Texas State University. Oluwasola is currently enrolled in the Mechanical and Manufacturing Engineering program, where he is pursuing a master's degree in the area of developing an electrostatic discharge material for 3D printing. He also has a bachelor's and another master's degree, both in material science. The title of his paper is Mechanical and Electrical Properties of 3D Printed PA6 Nanocomposites. Next on our panel is Dr. Pum Kim of Oak Ridge National Laboratory. Dr. Kim received his PhD in mechanical engineering from Georgia Tech. He is an R&D staff engineer in the manufacturing demonstration facility at Oak Ridge, where he uses his expertise in computational solid mechanics and additive manufacturing with fiber reinforced composites. Specifically, his research includes the design and process optimization of additive manufacturing and the performance prediction of printed parts with complex tool paths and geometries. Dr. Kim's paper is entitled Effect of Infill Patterns on Heating for Additive Manufactured Compression Molds. Also on our panel today is Dr. Eduardo Barocio. Dr. Barocio is a postdoctoral researcher at the Purdue University Composites Manufacturing and Simulation Center. He holds a PhD from Purdue University and a bachelor's degree in mechatronics engineering from Tecnológico de Monterrey in Mexico. His research interest is in modeling of composite manufacturing processes, as well as developing new composite manufacturing methods, primarily in the field of extrusion, deposition, additive manufacturing with fiber reinforced polymers. Dr. Barocio continues to develop the Composites Additive Manufacturing Research Instrument, or CAMRI, and the process simulation workflow for extrusion additive manufacturing, which he continues to support and develop. The final member of today's panel is Molly Carton, a PhD student in the Department of Mechanical Engineering at the University of Washington. She is a research assistant in the Seokpum Additive Manufacturing Laboratory, where she's developing new printing techniques and materials and computational designs for additive manufacturing. Welcome to you all, and thank you all very much for agreeing to present your work virtually this year. It's an impressive assortment of research, and we clearly have some interesting things going on in the field. We have some excellent technical questions already prepared for you, so we'll jump right in. And as just a reminder, if any of our listeners have additional questions, please feel free to submit them through the Q&A window in the Zoom control panel. So to start, Let's start with Anne. Anne, your paper on high performance materials for mass projection stereolithography talks about the post UV cure and oven cure. After this cure, after the post UV cure and oven cure, the BMI portion for the interpenetrating network still did not necessarily reach a high degree of cure. Can you comment on that? And is there anything that can be changed or improved to further increase that degree of cure?
Thank you for the question. So first, the reason that bismuth or BMI did not reach high degree of cure, because towards the end of the curing process, is high degree of network interlocking and greater diffusion limited effect. So the chances of bismuth seeing another molecule to react decrease significantly. There are a few ways that we can improve the overall degree of cure of bismuth. We can increase the final post-curing temperature. It was cured at 280 degrees C. We can increase it to 300 degrees C, and at higher temperature, it allows some chain motion that get more bismuth to react together. And we can also increase the degree of cure by during the printing step by increasing the exposure time per layer. This allows more reaction between BMI and acrylmorpholine during the print process. And as another way, we can also add additional chemistry to consume BMI, such as adding some allo compound that can react with BMI thermally during the post-processing. And I think lastly, we can also decrease the amount of BMI in the formulation, but just have to keep in mind that this will affect the thermal properties at the end. So there's multiple ways of doing that. That's it.
Excellent. The second question for you, this process for the post-cure for the IPN requires a long time, and it seems to be relatively complex. Have you done any work optimizing that cure process, maybe by increasing the degree of cure during printing, or could there be other ways that you could reduce the time?
So clearly in this study, we did not do the optimizing of the post-curing process. And I think pretty much this question is really related to the first one. I mentioned earlier that we can increase the degree of cure of both bismuth and acrylmorpholine by increasing the exposure time per layer during printing. We can, with that, we can get acrylmorpholine up to like full conversion. And by doing that, we can cut down the UV oven post-curing step. That is one. And we can also change a different catalyst for cyanoester that can initiate the reaction at lower temperature and shorter time. So I think if combining both of that, we can cut down the steps and the time for the post-processing.
How much time do you think you could save?
First of all, if we can cut down the UV oven step, that is 1 hour. And then if we use like a lower temperature initiation for cyanoester, and I think we can cut down like a few more hours. Say the total time might be 8 hours for post-curing compared with like 10 hours compared with before.
Excellent. Thank you. We have a question here, a general question for your digital design for voxel-based additive manufacturing. Could you explain to us just quickly, what is a voxel?
Hi, could you repeat the question again?
Yes, the question is, could you explain in more detail what is a voxel and what is voxel printing?
Okay, now voxel printing is before we continue to go to voxel printing, we should clarify what is a voxel first. And so we can say that as the voxel represents the material information on a regular grid of a on a three-dimensional space, and we can simplify as this is an extruded version of a pixel. So if we are thinking of a digital image, so digital images are consisting of pixels, and each pixel has its own RGB color code. So RGB color code, and those pixels are coming together and combining together, and we are getting our digital image, digital bitmap image. So as pixels has their own information, each pixel has its own information. Also, each voxel describes the material information of a solid part. And project printing technology currently capable of voxel printing, and with project printing technology, so anyone, any individual can characterize voxel, using the voxel printing and characterize material information such as rigid, flexible, opaque, and transparent materials. And then those voxels are joined together and stacked together in the software and to create the parts, and with large range of multi-material composite systems. Therefore, voxel printing allows any individual engineers, designers to control material packing as well as geometry freedom. And in our research, we try to investigate and we try to find a solution to what is the software and hardware compatibility. And because the hardware is not, it is in the still baby steps, and it needs to be improved. So how we can control, how we can provide the material parts integrity and quality by modifying the software and software design. And then after that, we analyze the mechanical properties of final composite voxel printed parts with same volume fraction, but having different inclusion size and distribution.
Excellent. Thank you. I think you actually started to answer the second question, so I think I might just allow you to answer this more generally. The other question we had for you is, what are the broader implications of this study? And I think you've started to address that. So maybe if you just want to talk a little bit more about what type of work might be coming in the future, that would be great.
Yes, as I mentioned before, in voxel printing, each individual voxel can be replaced with other voxels within the composite system and create material with various range of material properties, even without modifying the overall composition of volume fraction. So we can make we can optimize the design of the two multi-material parts without changing the volume fraction, and according to the application, of course. And currently there are research on voxel printing using manufacturing of customized prostheses and creating three-dimensional printed clothes in the fashion design. But what I'm thinking is voxel printing can be used broadly in composite materials manufacturing with its design freedom, and also optimize the properties according with respect to the applications. And actually what I'm working on to how we can enable this technology to control design of nano-engineered composite materials with optimized design.
Thank you. Questions for Oluwasola. Shala, in your work on mechanical and electrical properties for these PA6 nanocomposites, have you done any work observing the microstructure of the printed samples? And do you think voids inside the samples could affect the mechanical results, especially the strength? Would the void content be similar across all your samples?
Yeah, Eric, thank you for the question. So void could really be a major challenge in FDM printing. So the microstructure, I would think that the microstructure has little to do with that, but the most important thing is to evaluate the porosity of the material, which was not investigated in this study. So I would believe that the relative density of the theoretical compared to the experimental density of the material, would actually give us the extent of densification of this FDM material. So to answer your question, the extent of densification will actually be evaluated by the porosity studies, not essentially the microstructure.
So you use the relative density to determine how many or what the void content was.
So what I was trying to say is, like, we've not carried out the porosity study for this nanocomposite, but I'm just kind of thinking out loud and like attributing the void presence as like to evaluate the void presence. Then we might need to kind of carry out a porosity study to determine the extent of the densification of the material, like how dense it is, and by that we'll be able to know like the presence of void in the printed samples.
Sure. Have you done any microscopy work to look at the structure?
No, we've not done the microstructural study. We've not done because it's one of the recommendation of this work.
Okay.
So we actually tried doing the SAM, but we couldn't really get good images. But we will carry out a TM, which is a higher magnification study on the 3D printed samples to actually check the dispersion as well as the probably void content in the material.
Okay, excellent. Second question for you. Did you run your TGA experiments under a nitrogen or argon environment? And if so, or if not, the residual weight, should that be attributed to the weight of the carbon nanofibers? It seems like there's some inconsistencies across the initial weight ratios.
Yeah, yes, we run the TGA under the nitrogen environment at a flow rate of 50 ml per minute. And the residual could actually be the weight of the CNF, but this could only be ascertained by carrying out a TGA on the CNF itself, you know, to be able to know how it's actually degraded. So with this, we'll be able to know like the extent of degradation of the CNF, and if the residual weight could actually be attributed to the CNF.
Excellent. All right. Those are my two questions for you, Shaw. Thank you.
Thank you.
Next, we have Dr. Kim. Dr. Kim, on your paper, Effective Infill Patterns on Heating for Additive Manufactured Compression Molds. There was some heat issues with the mold. Did you try to insulate the side walls of the mold in your process?
Thank you for the excellent question. If I may share my screen. So I'm wondering if you can see the screen now. So we have not insulated the mold that side wall of the mold that we showed in the presentation, but we have done insulating on another type of mold that we printed, which I did not include in this particular presentation, but we have done it. So I'm wondering if you can see the screen right now. Can you guys see this screen?
Yes.
Okay, cool.
We can see the screen.
Right.
But there is a picture there is a screen open right next to it. There you go. Yeah. Right.
Yeah, that's right. So as you mentioned, Eric, we had an issue with the heat transfer from the bottom of the part to the surface, top surface of the mold. So we initially insulated the sidewall, but the temperature increase or temperature gain by insulating was not that high. So so we tried another method, which is we put a cartridge heater inside, and then apply heat through the cartridge heater. Actually, it's electricity heating through cartridge heater, and then we had some good temperature increase in the surface of the mold. So insulating did not really help much, but we found that cartridge heating helped a lot.
Do you think you could print in air passages like in the wind blade mold and then add a supplemental hot air heater to improve the thermal performance?
That's again very good question. So if I show this one, so we have printed a mold with hot air passages, as you can see in this picture. Well, at this time, it was not a compression mold, so there is not much pressure from the top of the mold, so it was possible to print air passages. For this application, though, it's a compression molding, so we will have a lot of pressure from the top surface of the mold. So printing with an air passage, which is basically a big void inside the mold, may not a good solution due to deformation issue. So that's the answer. But to increase the temperature of the mold, we are currently trying other methods to heat the surface of the mold instead of making a air passage inside the mold. So your question is very good applied to other types of composite mold instead of compression mold.
Okay.
Does that answer your question?
I believe so. Yes. Thank you.
Thank you.
All right. Dr. Barocio, in your work, design of composite compression molding tools, is it possible to simulate the durability of this tool? Do you have any ideas to what its lifetime might be?
Yeah, thank you, Eric, for the question. It's a really good question. So, I would like to just first kind of obviously clarify the purpose of the printed tools. We are using those mostly as prototyping tools. So you can do basically a short production run or a handful of parts with the printed tool. And going to the question, basically in terms of the simulation capabilities, we are able to predict creep deformation. So basically when we apply pressure and temperature, the fiber reinforced polymers will have a tendency to creep out, and the dimensional changes, there will be that result into dimensional changes of the part. So in terms of the durability, based on if we classify or we define durability in terms of the dimensional accuracy, we can estimate the shape change of the tool. But there are other aspects of the durability that could be like the surface characteristics of the printed mold. At this stage we are not able to capture those changes.
Okay. With this mold that you've developed, what's the maximum pressure that it can withstand?
So, I will, I guess, address that from the practical standpoint. So far we tested this mold with up to 1500 psi of pressure. However, that does not necessarily mean that is the highest pressure that this mold can take. This is a typical pressure we use for molding a composite sheet compound molding system. So that's basically just sufficient to have the material flow in the tool cavity, and certainly we can investigate the bounds of how higher up we can go in terms of the pressure using both simulations as well as practical. But for traditional compression molding applications, I think you can take the pressures that are in range of 1500 up to 2000 easily.
Could you maybe comment just quickly on what some pros and cons would be of going to a higher pressure?
So the higher pressure and obviously also higher temperature that result in more creep deformation of the tool, or can potentially result in more creep deformation of the tool. So that's one of the challenges in there. And also I will say the other challenge is as we are all aware, the printed materials are highly anisotropic. So one of the concerns with the printed compression molding tool is the tensile strength in the stacking direction. So depending on the print configuration and the design of the tool, that could result in large tensile stresses in the stacking direction that might cause or might compromise the tool. So that's why we need I guess we need to drive this. So that's why we demonstrated how we actually use simulation tools to drive that design of a compression molding tool, and that's the motivation. So there are considerations from the manufacturing process and the material by itself that go obviously into the design.
Excellent. Thank you, Eduardo.
My pleasure.
Small paper, mechanical metamaterial continuum materials realized through 3D printing using compliant mechanisms techniques. What are the applications for this soft robotics design?
Thank you, Eric. So for soft robotics as a whole, the typical applications are either when it's going to be interacting with, for instance, humans or living tissues, or when you have a delicate task. You can imagine why those would be places where you wouldn't want something hard interacting. So our particular interests were, for instance, robots where you have human interaction or human collaboration, for instance, in assembly tasks. So you might have a robot arm that comes down and does a part of a task while a human is doing a different part. Or on a much smaller scale, you might have a medical robot where it might actually have to go through a human tissue, and you want to make sure that you have a robotic part that can move without damaging any of the surrounding areas. So our particular design, we think, has promise for if you were to array it in a line, you could create something that could crawl through a narrow area because it can compress and expand. Or if you wanted to make a more three-dimensional object, something that could reshape itself in order to perform a certain task in a place where you would want to be very careful of your surroundings.
In your abstract, you talk about deployable structures. Is that kind of what you're just describing, or are there other applications where you would use this as a deployed structure?
So when I say deployable structures specifically, I might be referring to something that would pack very small and then could expand into the space to be able to do its task. So that is definitely one of the applications. But also, if you were talking about something that could, a robotic manipulator that could be of a certain size, pass through a narrow area, maybe follow a path that it needs to be able to follow, and then expand back out in order to do its actual task at its end location.
Okay, cool. Is it the printing with shape memory polymer alloys to actuate the moving parts?
I think that would be a reasonable thing to try. One of our targets was actually specifically to be able to actuate these with motors, and I believe that I said in the talk that part of the reason for that is because they're very well controllable. So, however, obviously a motor starts to be an issue when you're talking about something very small. For instance, the medical application that I mentioned earlier, that might be a problem, and that might be a target for active material actuation instead. I think another use for something like shape memory, using shape memory polymers in a 4D printing method for these would be to do the self-assembly process. So you might have a different actuation method, but that could be extremely useful for actually assembling these from a flat object into their 3D form.
Cool. Sounds interesting. I want to see one of these things in action. All right. You've been very efficient in answering your questions, so we still have lots of time left for bonus questions. I think what I'm going to do is I'll ask this question. It'll be the same question for everybody, and we'll just run right down the line, and everybody can answer. First bonus question: what do you say was one of the most surprising or interesting discoveries that happened during the course of your work? So we'll go back and start with Anne.
I would say most interesting thing that I found was bismuth limit is also a light absorber for this formulation. We don't really need to add any extra absorber to improve the print resolution. The reactant itself already does the job. And also another point is I think it's interesting that the printed part itself is in rubbery state. It has very low TG, but after post-curing, it maintains excellent shape and dimension, and also has very high TG and good mechanical properties.
All right, thank you. Dr. Ulu?
What I'm thinking is additive manufacturing is very capable of any modern manufacturing methods. So in our research, we saw that actually it's not only the optimization of your design, but also optimization of your material composition and material composition placement. So specifically, actually, it is not like, it's not included in my paper in SAMPE, but as a part of my dissertation, our research team was enabled to improve the thermal conductivity of a regular acrylic polymer by 20% by adding, by integrating of carbon nanofibers into a segregated region into a polymer using the Voxel printing design. So which is very successful. And what I was thinking, according to your application, that design can be changed with any modification, and it can be used anywhere.
Wonderful. Shala?
Yeah, I would say the most interesting thing is the manufacturing procedure, where we made use of the intermeshing co-rotating transfer extruder by Thermoscientific. It's an 11 millimeter barrel diameter, and it seems so handy. We were able to properly, tune the extrusion parameters to get almost 1.75 millimeter diameter for our FDM printer. So it's really very handy and very interesting to see how everything plays out.
Thank you. Dr. Kim?
Right. So I think the interesting part that we found here is that in general, like people usually choose their print direction based on printability. For example, if you print like this one, they determine the print direction based on what orientation will give the best printability. But this this direction affects the performance of the printed part, as well as within the given print direction, the tool path direction also influence the performance of the part. It has been speculated and it has been estimated before, but it's interesting to see that it indeed affects the performance of the part. Thank you.
Dr. Barocio?
Thank you, Eric. So I think one of the interesting findings of this work was the challenges, that printed compression molded tools have. So, for example, one of those challenges was being able to heat up the surface of it to the processing temperature of a thermoset dressing, thermoset composite resin system that we use. So basically, that exposed some of the challenges such as low thermal conductivity, even though it's a carbon fiber filled thermoplastic. We have a discontinuous fibers and relatively short fibers, and basically, still the thermal conductivity is dominated by the polymer. So there was a big challenge in coming up with creative ways to be able to reach the processing temperatures. So we investigate multiple of those potential mechanisms to heat up the surface of a tool using simulation. So before we went and tried out, we actually were able to, take some engineering decisions to basically make that compression molding process successful, and we were able to successfully produce a part. I will say the other interesting part is, how basically the pressures that we can introduce in a printed tool. And in this case, we got also surprised at how far up in terms of pressure we can go with a printed tool. And as I mentioned before, we were able to go up to 1500 psi to apply 1500 psi of pressure, and the part was molded at temperatures around 160 Celsius, which is really encouraging for for really pushing the boundaries of what we can do with 3D printed tools.
Excellent, thank you. Molly?
Well, I know that this is something that people always end up talking about with 3D printing, but it's kind of amazing to the extent to which making sure that the print process parameters really lined up, and especially when we were talking about printing joints and we were printing in TPU. So you think, oh, you just end up with a 100% solid rubbery object. It doesn't matter in which direction the print lines were and so on. But making sure that the print paths actually cross the joints in this way made a huge amount of difference to the success of our print. And especially just how much you could actually, how much movement you got and how many cycles that you could do before failure of any of those joints.
All right, thank you. A second bonus question here. This is the pretty standard. So what are you currently working on, and what are the future directions for this project? I think we'll reverse the direction this time, so we'll stay with Molly. I'll let everybody else think on their answer first. So where are you at with your current work, and where do you think this project is headed in the future?
All right. So I am working on something, a fairly similar project in the sense that we're talking about movable printed objects. We're talking about one of the things that we want to pursue is how you can array these kinds of objects to make a metamaterial. This is one of the conceptual things that we were talking about in the paper, but it wasn't something that we'd actually been able to pursue yet. And so that's something that I'm working on right now. And basically, how can you take this object cell that has this property where it can expand and contract and it's fully printed and so on, and actually build something that shows how that property can be used.
Very cool. All right, thank you. Dr. Barocio?
Thank you, Eric. So I would say the primary focus of our group is in the modeling and simulation of different composite manufacturing process. So in particular, in my group is composite additive manufacturing. So basically, our focus is primarily on expanding those simulation capabilities to capture different aspects of the printing process that for example, in our upcoming series of presentation from CAMEX. We'll be presenting, for example, some of our work in investigating how different types of substrate affect the residual deformation developed at the end of the printing process. So even though this is a problem that most of us have overcome, that are working in 3D printing have overcome, the parts coming off during the printing process. So basically, we've I guess put together a coherent way to simulate different scenarios by which the parts can come off, and basically kind of do a systematic study of how this affects the residual deformation of the printed part. And obviously considering, I have to say also that the simulation framework that we have developed, it's physics-based. So we basically, we measure the material properties at the level of the printed bead, and basically as a function of temperature and time, in the case of viscoelastic materials. And from there, we basically perform our process simulations. So as an additional effort, we're also expanding our simulation capabilities for different material systems, primarily fiber-reinforced thermoplastics.
Thank you. Dr. Kim?
Okay. So we have been working on actual printing of this compression mold, and then we measure the temperature of the surface, and we found indeed some difference in print direction with different molds with different print directions. So from there, what we want to do is we want to actually make the parts from it and see how much this print pattern affects the final part. That's more like an immediate goal. In the future, we have a lot of challenges in 3D printed mold, especially deflection as well as strength. So in fundamental scientific directions, we want to estimate or predict the strength of 3D printed part based on layer time, and also the molecular interactions between the layers. In practical directions, we want to expand this study from thermoplastic to thermoset materials. We have a large-scale thermoset printer in the facility. So we want to make compression molding mold and other composite manufacturing molds using thermoset printer, and then make parts from those molds. Those are more practical direction of the plan.
Wonderful. Thank you. Oluwasola?
Yeah, so the research direction would be like to investigate or to kind of produce FDM filament for like other applications, like magnetic properties application. This last study was kind of focuses on more of the electrical application. So we would like to exploit using the magnetic particles, to compound the thermoplastic, so that we could produce a multifunctional FDM material, for the FDM printing process. So it's going to be like a very good way to go, so that we could produce more multifunctional FDM printed filament for the FDM process.
Sounds good. Dr. Ulu?
Yeah, I just mentioned earlier about my last research about how we can improve the thermal conductivity of a regular polymer material by integrating carbon nanofibers in a selective region, selectively segregated region into a segregated region, and then what we are thinking to go next, like how that affects into the mechanical properties, and then how we can improve our software to optimize our design, and how we can generate our code and optimize that code. And thirdly, that we are thinking of what is the suitable way to suitable methods for the finite element analysis.
All right, thank you. And Anne?
So my current work, I work on synthesizing this interlinker, which has two functionalities, the two networks. So when the IPN is formed, they will be chemically linked. So we'll look into the effect of that on network formation and the properties. I will also look into the effect of secondary network for this type of IPN, see how compatible these materials are, and how much of the secondary network we can add in so that the formulation is printable. And lastly, is there an effect of the secondary network on bonding between the layers? And for expanding the scope of this work, I will be looking at developing different chemistry that involving high performance material.
Great, thank you. I am out of pre-staged questions. So my idea, we have a couple of minutes left. Do any of you have any questions you'd like to ask your fellow panelists? You're all working in the field of additive manufacturing. This would be a good time if something that you'd like clarified or just a little bit more information about. I think we have about a few minutes left that we could just open it up and let you guys discuss anything that you think is interesting. Anyone want to go first?
I suppose if it's a general question, I have one, which is where do you see additive manufacturing going in the next 10 years, since we're all sort of working on cutting edge research?
Anyone want to take that?
If I may start. So one of the major area I think additive manufacturing can shine is mold and mold industry. So additive manufacturing is a great tool to make a complicated shape, but in terms of mass production, its application is limited. But if you can make a mold from additive manufacturing and use that mold for making parts, then we can increase the productivity by order of magnitude, because the mold manufacturing itself is very time consuming and very expensive process. So in the next 5-10 years, I believe that mold applications from additive manufacturing is one of the major directions they can shine.
I would like to add as well that I think definitely additive manufacturing technologies, came to stay for a long time, right? But as we move forward, I think we are also developing more understanding of where it makes sense to use additive manufacturing, as well as on the bounds. Okay, what are the bounds of, let's say, if we call it mechanical performance, if we call it thermomechanical performance, how far we can go with this technology, and that is applicable, let's say, to the medical, to the tooling industry, as Dr. Kim was saying, as well as even for people working in the metal side, how far you can go, what is possible, and where it makes sense to make that. And I think the biggest challenge to get there is basically developing and making more widespread of understanding of the uniqueness of this process, right? Unlike the traditional manufacturing processes, one thing that we like to highlight a lot is how much the manufacturing process matters for 3D printing. You know, saying layer time, saying printing speed, printing pattern, depending on how you slice your geometries, the outcome you get. And that's a clear manifestation of the variability that you can get just from the manufacturing process. So I would say that's my contribution to that question.
Thank you. Anybody else? All right, I think we're at about that time. Final call for any last statements from anyone? All right, if not, I'd like to thank you all very much for participating in the session, both our panelists and our attendees. If you do have additional questions, please feel free to fill out the form on the track landing page on the SAMPE North America website, and SAMPE staff will follow up with your questions. Make sure to check out the content that's being released next week for the emerging technology and inspection and repair tracks within our virtual series for SAMPE this year. So again, thank you all for joining us today and sharing your time and expertise for this session on additive manufacturing.